Uh,
Yeah, I'm glad it works well both the ways, because I think the
yeah.
students need to know, and you are really keen at putting your extra mile to answer those questions, not only immediately when it's asked, but also the next time with
Well,
of slides for that. So really thankful to you for that.
that's what I enjoy. In fact, I like questions to be asked and then gives me a little bit of food for thought. And I
Mhm.
sit down, look into the answers. Because at the time when they ask a question, suddenly, the question answers may not be that visible
Mhm.
also, and it's difficult to explain the things. Then I
Mhm.
just put down the things together. In fact, this is what I was doing for NAL and EDA also, like
I
that.
see. Okay. Okay.
So, in fact, I found those people because they are engineers and they're used on the practical problems. So their
Mhm.
questions used to be a bit more involved, and I had to then sit down a couple of days uh,
Mhm.
to prepare some answers. So I really enjoyed with them. I found the excellent people over there in NL and EDA.
Mhm.
The very knowledgeable, very good engineers we have. I think I find our Indian team engineers are pretty good in the quality.
Mhm. Mhm.
Your ISC has been famous always for the quality, of course.
Mhm.
And so
Yeah,
India
I
to
can feel the pulse of what you're saying, because I frequently tell some of my students who become profs at IITs, teaching is the best way to learn,
yes,
especially when
yes.
we have these bright students around asking questions. There's a lot that we can learn out of those questions and trying to answer those questions. So
Yeah.
I'm glad you are in the same wavelength.
Say you see NASA Langler is a center where quite a few old IIT, ISC Bangalore people were there.
Hmm.
I think you might be familiar with IS Raju, used to be
Oh
AK.
yeah, yeah, yeah. I
IS
know.
Raju and
Exactly.
Professor Dr. Pamadi. He, of course, was passed out from ISC Bangalore, but he joined IIT Bombay. Then
Hmm.
he went to NASA Langley, and
Hmm.
he retired only a couple of years back as a head of the aerospace sciences, in fact.
Hmm. Hmm.
Very, very knowledgeable person, and he has
Hmm.
written a book on aerodynamics.
Hmm.
Mm. Lots of people actually in said Dr. Shivaram Krishnan, who is also IIC person, who was my colleague at IIT Bombay. He's
Hmm.
at NASA Langley, he went, and for last almost 40 years he has been there.
Hmm.
So there are lots of people from IIC Bangalore that's
Right.
produced some great people.
Right, right, absolutely. And last year when we had this Vaishvik Bharatiya Vaigyanik Vaibhav Summit by the Prime Minister's office, we had literally hundreds of people in pretty much every aerospace field. We had a month-long event, and every day programs used to go for 4 to 6 hours, and so much of contribution from some of the real big names in the aerospace industry, and all of these were NRIs or PIOs or OCIs.
Yeah, that's right.
Amazing what kind of contributions we have made. Probably it's not all documented together, but individual stars we've known about.
That's right. It's a great contribution. Somehow, quite often, what happens, the contribution is not well recognized,
Hmm.
even
Hmm.
though they are forced behind a lot of innovations,
Hmm.
technology. Say in Boeing, actually, Boeing has plenty of Indians working.
Hmm.
Boeing, Seattle,
Right, right.
everywhere in Boeing companies, plenty of
Hmm.
Indians working at good, high positions, doing a pretty good job.
Hmm. Hmm. Yeah, as I mentioned earlier, we are a strategic partner with Boeing, one of the 5 universities around the world to be that.
Hmm.
And so we work closely with what used to be McDonnell Douglas Phantom Works in St. Louis, now the
Yes.
Boeing there. So we visited that quite a few times, and there are quite a few Indians there as well.
That's right. And Boeing has R&D one team over there
Right.
in India, also Bangalore, is it?
Yes, 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 they do. Yeah.
Mhm.
Hyderabad also.
Hyderabad. Okay.
Yeah.
All right. I
Yeah,
think
let's get going.
high
Yeah.
time we can start now. So uh, let me start sharing my
Yeah, please.
screen, open share tag, and let's see which is my presentation. Okay. Good afternoon, everybody, and it's the third lecture of the series of lectures. And before I start my certification lecture, I think I would just try and show some of the answers to the questions raised during last lecture. Can you see my presentation now?
Yes, we can. Please go ahead.
Okay, now, so some of the answers actually, one question was raised, okay, we showed WFD's MED, MSD for metal key structure, how it is applicable to composites. Now I said damage propagation due to fatigue. Also, we know composites are not sensitive to that fatigue damage propagation under cyclic loading as the metals are, and of course of composite philosophies and no growth of damage generally. However, what happens usually the delamination could be a problem, and especially for the structures which are more relying now, and a lot of structures are being developed as a co-cure, co-bonded, integrated structures, like you would have a co-bonded or co-infused, co-cured rib with one of the skins or the spar with one of the skins. A lot of work is being done. I think even NL has been doing a lot of work on such structures and around the world. And one side could be fastened, another side could be bonded, like what you see on the screen. Some of the issues with this one, I could discuss this issue for a long time, but I don't have time to discuss that currently. Could be, we could recognize, okay, WFD for such a structure could be, there could be delaminations or bond line failures at a couple of places, and then during the fatigue, these delaminations or these bonds could grow and try to merge together to form a large disc bond. So this could be considered another WFD, widespread fatigue damage. In composites, another scenario could be similar, of course, similar to the previous slide. You have the stiffeners which are bonded, co-cured, generally co-cured, or could be co-infused, and they could have some disc bonds at localized positions, and then during fatigue, they could grow on various elements like stiffeners and join together, and they can disbond and fail these stiffeners, and then structural integrity will be of a issue. Same thing could happen. You see what some typical structure, we have the skins joined together. At the trailing edge, I have shown it has to be a double countersink fastener, because you need a aerodynamic surface on both the sides. And generally what happens, these double countersink fasteners always problem in the trailing edges joints. And there's a possibility under cyclic loading, these fastener rivets, we don't call them rivets, we call them fasteners, double countersink fasteners. So they could fail, and some under cyclic loading, emergency situation, high cycle fatigue, like the flap being an engine environment and having a very high cyclic fatigue loads, and it's possible some of the fasteners might fail if they're not properly designed. And once they fail, again, they can start unzipping the trailing edge. So this is another widespread fatigue damage in the composite structure. I could, list many of the other scenarios for such damages. However, this is just examples I've tried to show to justify, okay, the WFD is not only defined for the metallic structures, but equally valid for the composite structures in various scenarios. All right, I won't go into the details of this one. Next, another question was asked, okay, some guidance on the riveted joint, so normally in composites, we never use rivets. Okay, so suppose using the thin sheet metallic structures where rivets are used for fastening. I won't go into the details of this. Again, rivets are suitable thin metallic sheets joining, and rivets not suitable for composite structures. As I said, we don't use rivets in the composite structures. So the requirement for a countersink so the knife edging is avoided is T1 must be greater than 1.5 H, or H by T is less than 67%. Normally we design the bolted joints or riveted joints so that the countersink does not cause a knife edging. Another requirement, which has been put by Michael New. Normally we don't use this requirement, but I've quoted it. Michael New in the book has mentioned this one, and normally we design all our structures with this requirement. Okay, now I won't go into the details of this because if you see the next slide, I've said separate lecture to be delivered for bolted joint. I've got about 150 slides for the bolted joint, and if there is time, although I had committed to Professor Dinesh the bolted joint, and depending upon the time permitted, I will consider there, and it's very interesting aspects because joints are very important in the structure. And one has to be very careful designing the joints. So I would take up all the issues about the bolted joints for the composite structures later on. A bond test, somebody asked some guidelines on the bonded joints. Okay, I've just put up very shortly because bonded joints itself is a big subject and I could have a lecture on that. Just for their qualitative tests, which I have put over here, because normally if you want to quantify the strength of an adhesive, it's very difficult to find a coupon, which gives you a good adhesive strength, which is representative for the structure. There are a lot of issues with these coupons. They are just used as a qualitative test to compare from one adhesive to another. Even then, it might be difficult to compare from one adhesive to another using these specimens. When you load it, this specimen, if you can imagine, because of load eccentricity, it will bend over here, create a lot of peeling failure. So ASTM D1002 single lap shear test can be used compare between one adhesive to another. This test does not provide realistic shear strength for the bond line. However, even for comparison, data should be used with caution. And you can just look into the ASTM D. I can send you the copy later on, or you can find in your library if you can find, this ASTM. I've never used these coupons, by the way. Apparent, and oh, sorry, this F should not be there, sorry. But this is another test where at least this is better than the previous one, was 002 in the sense, at least you can avoid the eccentricities by putting a doubler, bonding the doubler, and then loading in tension. It provides you the shear strength. However, still it develops some peeling action, peeling stresses. So this test also is not that reliable in order to give you a good shear strength of the adhesive. However, again, this is for comparative purposes. And when you want to compare in that as a receiving test for the material, then these tests are used. But we do not use the data from these tests for the design. If you want to use it for design, normally rough design, probably we'll apply a safety factor to the value obtained from this test. Another test is, I have not drawn whole of the picture, thick adherent test. This is quite commonly used in order to assess the stress-strain behavior for the adhesives, shear strength to strain, shear stress to strain behavior to determine the shear modulus, and usually then determine a bilinear curve for the adhesive. And the test is expansive. You can read this in ASTM 5655, and I cannot go into the details of this test because of limitation in time. Then our preferred approach normally is this one. Rather than the strength approach, as I mentioned last week, we would use in today's time the fracture mechanics approach for the bonded joints, not the classical strength approach. So current practice to analyze the adhesive bonded joints is based on fracture mechanics. Initial flow of length A is assumed to exist at bond line. Normally, it would be like a 6.4 millimeters long and full width. So, and fracture analysis is performed for mode 1, mode 2, mode 3 to determine bond line integrity. And at present, I may not be able to go into the details of mode 1, mode 2, mode 3 failures. This could be another lecture. And in order to generate the fracture toughness, because these are real reliables then for fracture toughness, fracture mechanics approach when you want to use. Using a double cantilever beam specimen, determine G1C, mode 1 fracture toughness, and edge notch fracture G2C, and usually the mode 3 value we would normally consider equal to mode 2, because mode 3 test is difficult to perform in order to determine G3C, and it is the usual practice, because that is also a shear mode, G3C equal to G2C is assumed. And I've shown roughly the schematic coupon over here. Normally this coupon is 12-inch long, and the thickness could be about 2.5 millimeter to 3 millimeters for DCV, and same coupon could be used for ENF, which is called edge notch fracture, and this is 3-point bend test. Equations are provided in any of these methods document. You could look into the NASA or ASTM. These are very tricky tests. Let me tell you, what you will find from the ASTM standards using these tests is still you might have to manipulate or juggle around to find really the initiation, and it's not easy. It looks simple, but when you are trying to determine the right value of G1C, because you find lots of scatter when you have analyzed the data for G1C and G2C. And then you have to fix up your criteria. What is my criteria in order to define G1C? Initiation or 2% growth or 5% growth, those criteria, I tell you, you will find a lot of variation in that. So it's a bit tricky to interpret the data from test for this coupon. However, that's the way it is done now. Any questions on this? Discussions for the persons who asked the question? No response. Okay, somebody asked about this 12-inch, and I said I would be talking about in the damage tolerance. I would make it more clear, but here I've just provided something which I'll be considering when I'm taking my certification lecture for damage tolerance. So fuselage structure, the design requirement is that a commercial transport aircraft fuselage must be damage tolerant to penetrations in the present pressure shell up to approximately 12 inches. And that is what I showed last week when I showed the fuselage requirement. Now, so that means this residual strength should be at least the limit load carrying capability. Then there is another subsidiary requirement that when the damage starts propagating, it should be stopped within 2 frames. Okay, so 2-bay crack is the standard design criteria, and the load requirement would be around get home load for this one. And this is a must, whether it's a wing, fuselage, any stiffening structure, 2-bay crack requirement is the residual strength requirement for the stores. Okay, next one. What did I have? Cabin noise. I'm not very familiar about this subject, and I do not really did not understand the question properly, whether it was the cabin noise source reduction. If the person who had asked a question could elaborate on what question
Sir, actually, what I meant was like the sound attenuation offered by the composite structures is less compared to metallic structures. I have read in one of the articles. So if that is the case, for the same external noise which occurs due to aerodynamic noise, whether the cabin noise means interior of the airplane will be higher, and if so, it will affect the human like comfort. That was the point I was asking.
Okay, now if you look into the current transports, in fact, 787 is fairly quiet, in fact, and this noise consideration has been there because sources of noise are many due to the engines, the boundary layer, effect turbulence boundary layer, the interior air conditioning systems, working pressurization, all that, and they have been considered. And there's a noise absorptions. Yeah, but I'm not very familiar about this, but I could look into now. You have elaborated the question a bit more, and next lecture I might try to look into a bit more carefully and try to answer your question.
That's okay, sir. Thank you.
Mm-hmm. Okay. So was there any other question from the previous one which I missed out? Anyone? Or are the persons who asked the question satisfied with these answers? Okay, if there's no concern, then I could stop this presentation and let me try to share the next one. Can you see this presentation now, the certification one?
Not yet, Dr. Garg.
Not so. That means let me go to the tray again. Meeting. So share. Stop sharing. Share open tray. Okay.
Yeah, we can see a slide titled fail safe.
Okay, so this is the one which I've forgotten where did I stop last time. I think I stopped at this slide and then we said we restart fatigue and damage tolerance. Did I show this slide last time or no? I'm confused because I was delivering lecture to IIT Kharagpur also people last week. So I've forgotten which slide I stopped here.
No, this slide was not discussed, Dr. Garg.
Okay,
I think we can start from here.
Yeah, I start from there. So structure fatigue and damage tolerance. Now, fatigue life philosophy. And this is important to consider the various philosophies like safe life we talk, fail safe we talk, damage tolerance. And what is the difference between these three? And basically, if you remember last week when I was talking about the various historical failures and how the approach for certificate changed, because initially, say when Comet failed at that time, the desired approach was safe life. After that, in 1978, fail-safe requirement came up. Oh, sorry, not 50, sorry, 78 damage tolerance came up, but after the Comet failure, the amendment was in mid 50s when the fail-safe was introduced, and then later on, when another failure of aircraft occurred, then even fail-safe was not adequate and damage tolerance requirement. So after 78, it's a damage tolerance requirement. Okay, now what are these fail-safe, safe life, damage tolerance requirements? What you see here, safe life means the structure remains crack-free for the period of life, whatever you have predicted to occur, whether it's a 1 DSO or 20,000 flight, after which the part has to be retired, and so on. So it's a limited life, crack-free. You can't expect any damages over there during the service. You have to retire the part. Fail-safe, which is a redundant. So what happens here? You have a redundant load path. multi-load path structures. One of the load path fails. Still, the structure is able to carry the limit load until the next inspection interval when the damage is detected and repaired. So the requirement would be for a fail-safe condition to tolerate the limit load for 2 inspection intervals before it's repaired. Damage tolerance, and this is the current approach for all these structures, which is safe, slow crack growth, and then residual strength requirement, and also then the inspection intervals. So these are 3 elements of the slope, damage growth, residual strength, and the inspection intervals you have to define. However, the issue with the slow damage growth is in metals. That's fine because you can determine, you can predict the life or the number of cycles within which the initial crack will grow to a particular length. However, that damage growth prediction is not possible for the composites. So there are like hundreds of publications are available, but people have tried to predict the damage growth in composite using several different methods, and still that it's not a reliable or easy solution. That's why the current approach for the composite structures is no damage growth approach. We'll talk about this in more detail. Okay, yeah. So I just quoted a few paras from 571 requirement, safe life requirement. Fatigue safe life evaluation, compliance with the damage tolerance requirements of paragraph B. Paragraph B is damage tolerance. Of this section is not required if applicant establishes that their application for particular structures is impractical. What it says is, if for a particular structure damage tolerance is not possible, then safe life could be used. That is inspection not possible, as I had shown last week in that the failures diagram. This structure must be shown by analysis, supported by test evidence, to be able to withstand the repeated loads of variable magnitude expected during its service life without detectable cracks. And appropriate safe life scatter factor must be applied, of course. All right, so safe life, how 571D, this AC, defines as per 14 CFR AC 25711D, safe life is a number of events such as flight cycles, landing or flight hours, within which the structure has low probability of degrading below its design ultimate value due to fatigue cracking. So component or systems is designed to not fail or remain crack-free within a certain defined period. That's what it says. It should not develop any crack for the defined period for which you have designed the part. Okay, this is what I have diagrammatically shown when you are trying to justify the structure based on the safe life. So here what you see, the residual strength capability, and this is cyclic loads. We define, suppose you have tested the component for end test, it says the residual strength after that end of this end test should be above DUL, which is design ultimate load carrying capability of the structure. And then you will define the safe life is equal to end test divided by SF. And generally SF for metallic structures could be around 3 to 4. So basically, suppose your design life, you want to design a structure for 20,000 flights, you'll have to test for 80,000 flights in order to justify that 20,000 flights life. Okay. Now, in spite of all that, this slide shows, in spite of that 4 times or 5 times safety factor, the structures have failed earlier than that. And this table is evidence of that. I have taken for this, they're all fighter aircraft, where you see KC-135, design safe life, 13,000 hours. However, what you see, 14 cases of unstable cracking lower wing skins between 1,800 to 5,000 hours. Lower wing surface were reskinned at 8,500 hours. So what you see is, even though the structure was designed for 30,000 safe life hours, it didn't stand that. Next one, F5, 4,000 hours design. Fatigue failure of lower wing skin root region at 1,900 hours caused loss of aircraft. Serious. F111, 4,000 hours design life. Fatigue failure of center box at 105 hours caused the loss of aircraft. Fatigue failure was caused by a defect in D6 AC steel center wing. This is brittle steel and this is nasty. What happens, there could be a minor defect which you can't inspect inside, and then that defect could be fatigue critical, causing the reduction in life significantly. And that is why safe life is not a reliable criteria based on these examples. And there are umpteen examples. Basically, when safe life designs have failed prematurely. And so failure of 111 caused US Air Force to issue MIL A 8344 for damage tolerance requirement for all US aircraft July 1974. In fact, this requirement came before FAR requirement. FAR requirement for damage tolerance came in 1978, while the military aircraft US Air Force issued in 1974. Now, this MIL 83444 document is obsolete document. Now that has been replaced by JSSG 2006, which you will find in my references in this document. You can download that from internet, free. It's interesting. And basically, because suppose you want to understand military airplane like Tejas, it may be an interesting document to understand the certification philosophy. Most of the criteria is similar to FAR transport aircraft, but there could be some differences. Issues with safe operation, I've already talked. I think I won't go into the details of this. Now, fail-safe requirement. The definition for 14 CFR AC 25571D, fail-safe requirement is the attribute of the structure that permits it to retain its required residual strength for a period of unrepaired use after the failure or partial failure of a principal structural element. When one of the elements fails or partial damage occurs to the structure, the remaining structure will not fail within a specified period of time. And residual strength with element failure regulatory greater than regulatory required load. So what happens, as I said earlier, the fail-safe, one of the members fails, and it could be detectable damage. However, you don't repair immediately. This damage should be able to be sustained for 2 inspection intervals without reducing the residual strength below limit load. So that's when I've said here regulatory required load, normally it is a limit load carrying capability. It should be, so residual strength with element failure must be greater than limit load requirement. That's a requirement. The feature safe life fail-safe continued features multiple load path consisting of multiple elements of crack damage arrest structure, single element or obvious partial failure, redundant load path, regulatory load capability after element failure, which is normally the limit load carrying capability. The damage shall be detected and repaired during normal maintenance inspection or operation of an airplane prior to the failure of remaining structure. Okay. Now, what is damage tolerance? And this is what the main focus would be of our investigations. As I said, current structures, in majority of cases, it's mandatory to design the structure with damage tolerance capability unless we can't meet the requirement of damage tolerance and then go back to safe life. So the attribute of the structure that permits it to retain its required residual strength for a period of use after the structure is sustained given level of fatigue, corrosion, or accidental or discrete source damage. Safety is the primary goal of damage tolerance. So you can see from this diagram, you have certain damage and you are supposed to design the structure with certain damage length or diameter to carry the required residual strength as per the regulatory requirement, which varies depending upon the size of the damage. Okay, why damage tolerance? Damage tolerance is the design philosophy used for maintaining the structural safety of the aircraft. That is the major reason for designing the structure for damage tolerance. Safety is the primary goal of damage tolerance. Safety, safety, safety. All commercial transport aircraft designed after December 78 are required to meet the damage tolerance requirement per 14 CFR 25571. Okay. Now, this is an important diagram, which I think is a good idea to understand what it tells us. Basically, this diagram is the key for the design of composite structures. So what this shows, the y-axis as the residual strength and x-axis as the damage severity. You look in the first category damage. Now, the category 1 damage is undetectable damage. There are lots of damage like barely visible damage or manufacturing flaws like delaminations. You have the entity capability that they can't detect the delaminations or disbonds in the structure for less than a quarter inch or 6.4 millimeter or 7 millimeter, depending upon the probe. So that means those damages could always remain because it's beyond your inspection capability. Then in the factory, there could be some damages like a BVIDs. Unfortunately, in metal, of course, if there is a tool drop or some hailstone drop, some impact damage, on the surface in the metal like aluminum, the damage will be visible. Unfortunately, in composite, the damage you could have caused the damage by impact, but on the surface, the damage may not be visible. And that's a typical of composite structure. However, that impact would have done enough damage to the internal plies in terms of the disbond, delamp, fracture of fibers, cracks. So the requirement is the BVIDs. I'll show in the next slide what are the BVID, VIDs, and all that categories. But certain small damages and the hole, like quarter-inch hole. So all those small damages which can't be detected, considered undetectable damages, have to be considered for the life of the structure. And then if we are considering the damage will always remain in the structure, that means our load carrying capability of the structure must be at least the ultimate load carrying capability, above ultimate load. That's a design load is ultimate, and those damages should be able to be carried for the life of the structure at ultimate load. However, of course, when you are doing a margin equal to 0 at certain critical position with the loading more, at other regions, margin could be more than 0. And that is why you find here, I have added a note over here, MS. MS is nothing but margin of safety equal to 0 at DUL, design ultimate load for ADL. So what happens, what is ADL? ADL is allowable damage limits. Now this is useful for the repairability of the structures. Suppose you have a flap and you are having a layups, layup thicknesses are varying and layup percentage is varying like 0 depending upon your load carrying capability, loads on the structure. So thickness on the layups could be varying. However, what happens, you can't just continuously vary everything to suit the load requirement and keep the margin zero. That's not feasible. There would be some areas where you have designed the structure to be margin to be zero, and other margin could be 0.1, 0.2, or 1 even in some regions. Because loads are not uniformly distributed on whole of the skin. Although you are changing the layups thickness, you can't just optimize everywhere to make the margin zero. So what happens? Okay, the margin is zero at certain location of the skin, but remaining is some location of the margin could be 1.5. What happens then when we do the margin survey after margins calculated zero? Then we try to determine, okay, if the margin is 1 at this particular location, and that margin 1 is defined for a 1/4 inch hole, then can I tolerate 1-inch hole in that? And so I recalculate the margin equal to 0 for a particular damage. What is my maximum damage? Which will give me the margin to be 0, because initial margin for 1/4 inch hole is 1. Okay. And that is why what happens, we do the margin survey once after designing the structure so that we can divide the structure into several zones for the repairability. So in a particular zone, we'll say only 1/4 inch hole is permitted. In another zone, we can say up to 1 inch. If in service, the structure gets damaged and it creates almost like a 1-inch hole equivalent damage, what the airlines can do, they don't have to immediately repair the damage. They can put some high-speed tape, flight, and then when during the next inspection interval, they can repair the damage as permanent repair. So that is what the advantage of this allowable damage limit is. This is for the maintenance or repairability of the structure. We provide the guidance, divide the structure in various zones. Okay. Now, so as the damage is increasing, so naturally the damage is increasing in the structure, depending upon the severity of the damage, your residual strength would also decrease. What we are defining here, detectable damage. Detectable, walk around inspection you have, and like a indentation depth could be, I'll show again in the next slides, a bit higher than 10 thou or 0.25 millimeter. It could be 1 millimeter deep dent. Hole could be larger, like a 1-inch hole, 1.25-inch hole, which is detectable. So, and residual strength of that, we want more than limit load. It's a big range over here. Detectable, then we are calling readily detectable. What the readily detectable means, the damage should be detectable easily within a few flights. So we can divide this into different regions. That means we have to do analysis for this higher than limit load. And at this CDT, we are defining at critical damage threshold, at which we define the margin to be 0 for the design limit load for CDT. That's the definition. And then we are defining here some damage which is really readily detectable boundary or obviously detectable, that immediately is obvious. If you are just walking out, one can just see from a distance, okay, that's a large damage like a 6-inch hole or 8-inch hole. So, however, what you see from this diagram, the load requirement, residual strength requirement is below limit load. However, this point is difficult to define. In fact, sometimes it's defined the load per flight or during once in a lifetime of the flight. That's a limit load, less than limit load, and limit load is defined once maximum load obtained during the fleet lifetime. So, however, as you see, the block I have written here, preferable for design, to design this point. In fact, in certain damage tolerance diagram, this point is defined as a limit, designed limit load. So they define 3 zones. One, ultimate, they draw like this. come here, and this point, this shifts over here, or I define this as a limit load over here, and then this is a get home load over here. So we consider all this damage. That means right up to this, like up to like a 6-inch hole or like a 12-inch crack in the fuselage could be defined to carry the limit load carrying capability rather than this one. Okay, so we design it because otherwise the structure design becomes more complicated, loads become difficult. And then we come to this one, immediately obvious. What it means, this is called discrete source damage. So this term, which is MDSD, maximum discrete source damage. What it means, when the aircraft is flying, due to the bird impact, that's called discrete source damage. The damage could be occurred due to a bird strike. There have been lots of cases when damages have occurred due to bird strike. Then there could be turbine blades failing, rotor failing, and it fails, it hits the aircraft structure. It could be wing, it could be trailing edge surface, so depending upon the directions, and it can create a damage. So these are discrete source damages. In this zone, category 4 damages, they are known to the pilot when it occurs. And the only requirement for that is below limit load, which is normally around 70% of the limit load, which I'll show in the next. So let me just define, make it more clear. Hi, any question, is it?
Yes, Dr. Garg.
Yeah, okay.
The previous slide.
Yeah.
What is MDD on the x-axis?
Which one?
On the x-axis.
Yeah.
I see MWD, the second one, yes.
Oh, maximum design damage.
Maximum design damage, is that?
Yeah.
Okay.
We normally don't worry about this one, actually. These are terms provided in Act. Normally what happens, we design with this BVID, large damages, and this one.
Yes, Dr. Garg. One more question in this is, when we refer to detectable and ready detectable damages, are we talking about to the normal human eye, or is it through any techniques?
This is all visual inspections.
Visual inspection. Okay, thanks. Yeah.
In these, none of this is to be using any microscopes or any magnifying glasses. It is just walk around inspection. And that's the criteria for composite structures. They all walk around inspections.
Okay, thanks.
And that is why this damage, I'll show you in the next slides, almost like 6 to 8 inches whole, 12-inch crack. Back big.
Right.
Okay, now category 1 damage, non-detectable or barely visible impact damages. This is designed to design ultimate load. Category 2, detectable damage. Damage is detectable with a high probability during walk around. Requires repair per inspection process when they are detected. That is after 2 inspection intervals. Because you don't repair every time the damage is found, you will just ignore if the residual strength capability is higher than limit. Design limit load until defined inspection interval. That is 2 inspection intervals normally we define. Category 3, obvious, readily detectable within a few flights. When such large damage is there, like 6 inches, depending upon the criteria. In fact, I'm just quoting 6 inches, it could be 4 inches or more. Readily detectable within a few flights of occurrence. So what happens in this one? This damage doesn't have to wait for inspection intervals. It is when during walk-around inspection, such a large damage is seen, aircraft will not be allowed to fly until repair is done, in this case. Damage, 2 inspection intervals, but this is only within a few flights of occurrence, so requiring immediate repair. So that is the difference between category 2 and category 3 damages. The repairability. So limit load back. Yeah. Yes.
So Can we just go to the previous slide once? 1 second, please.
Yeah, sure.
Okay, sir. Right. Sir. No, I just wanted to note it down. Right, sir. Thank you.
Yeah. You already presentation is with you. You can just see. And if you want more details, in fact, you can read this document, AC 2107B. The next one. So this is obviously detectable damages within a few flights of occurrence, requiring immediate repair, because that's a requirement. Aircraft, once it's detected, aircraft is not allowed to fly until the damage is repaired and returned to the ultimate load carrying capability. That's another thing. When you repair the damage, the strength after the repair must be ultimate load carrying capability. There is no reduction in that load carrying capability definition. Repair must be as per the new structure capability.
Excuse me, sir, I have a question.
Sure.
Actually, sir, when you're saying requires immediate repair, how exactly is the repair done? Because in case of composite structures, the parts are fewer, right? So do you just fill in the cracks, or I'm not understanding how the immediate repair is done?
You're asking for me to define, okay. That's a, depending upon, suppose there is a damage, suppose you have a skin. Your skin gets damaged. Then you have to repair like a scarf repair. Let me just try to find a slide if I can find to show you. In fact, I've done a lot of work on the repairs. I'm not sure. Let me see if I had put in ADA, lecture to ADA.
Sure, sir.
Question answers. Okay, let me just try to show you this presentation. Stop sharing, open try. Can you see this? Let me see. Bonded structures. Yeah, so suppose you have a skin. Let me just show you that this, of course, written for. Suppose you have this, consider this is skin. and there's a damage. Now, of course, normally you won't have such a sharp damage. In metals, it's okay. In composite, the damage could be like a hole or damage. Anyway, so what you do, you remove that damage, smoothen it out, scarf. Normally, we do the scarf repair. And the scarf repair is shown over here actually in a section like this one. So you have a damage. This was the amount of damage. But when you are trying to lay up the plies, you can't just make the straight repair. So you will scarf it. Normally the scarf angle is 1:30, we consider. For thinner structure, it could be as much as 1:50. Otherwise, around 1:30 scarf repair. And I could talk about that, but again, it's a detailed subject for the repairs. And we lay up the plies. So that means this is our pristine structure and these are repaired plies, and we put a overlay ply. So this is a normal scarf repair. So I've just shown like this one. So this is your every ply, and then you are putting the repair plies like this one with the adhesive. So normally this is a scheme. Another step layup. Normally we use the, rather than the step, we use the scarf, what I've shown you there. This is just showing a coupon, which normally we consider in order to justify the repair. I've done a lot of work, in fact, on the repair justification. So we would consider fraction mechanics approach rather than the conventional strength approach. Like I talked about the bond line fraction mechanics approach, and I'm very conversant about that. So this I developed this methodology, in fact, for the fraction mechanics analysis some time back. Okay, now I can't go into the details because it's again a big subject for the repairs of these structures.
Yes, I got it. Thank you.
Okay, that's interesting. So now let me just consider. Okay, now this one. So category 3, category 4. Okay, you can see this presentation now? Hello?
Yes, sir.
Okay, so category 4. So in that diagram, I said category 4 damage, which is discrete source damage, which occurs during the flight, and the pilot or flight crew knows when it occurs. So the causes of the damage could be bird impact, uncontrolled failure of engine, fan blades, high energy rotating machine, sudden decompression of compartment, requires repair before next flight. Design load carry capability, according to the requirement, is maximum loads expected during the completion of the flight and 70% of limit maneuver loads and 40% of limit gust load combined with maximum appropriate cabin differential pressure. Part 25571E. Okay. So these cover, of course, definition of various categories of damages, and I would recommend those of you who are interested in reading a few more details, you could look into the AC 2107B, which defines in detail these damages, or Mainland Book 17, Volume 3. Okay, now structure damage tolerance requirements from the compliance point of view. And if you remember previously, I defined two types of structure. One is principal structural elements, another is non-principal structure. So you can consider like principal structural element to be a primary structure and non-PSC is like a secondary structure. Normally, we don't call primary secondary. According to 5711D definitions, usually you call PSCs and non-PSC structures. That's the usual definition these days. So damage tolerance when you are trying to satisfy the requirements for PSE, which is critical structures, you would consider the damage tolerance per 14 CFR 571. That's what we have been talking about, the damage tolerance in zones A, B, C, D. Oh, sorry, category 1, 2, 3, 4. Out of which all categories 1, 2, 3, 4 have to be considered for this one, primary structures. Whereas when you are trying to justify non-PSEs, then this criteria is not applicable. 571, not required. Only category 1 damage tolerance diagram required. That is only BVIDs, very small damages, that is undetectable damages, but not the detectable damage for non-primary structures, non-PSEs. So, okay, now what is durability? We talk about the durability. The durability is the ability of the structure to resist cracking, damage growth due to corrosion, hygrothermal degradation, delamination, wear, and the effect of foreign object damage for a specified period of time. Normally what happens in durability, we consider, okay, damage doesn't initiate. So durability addresses largely the economic issues. Damage tolerance addresses the safety issue, and durability addresses the economic issues. Difference between damage tolerance and durability I have tried to show in this slide schematically in a simplistic way. So durability often addresses the onset of damage from the operational environment. Okay, so what you see, the damage size versus the damage propagation. Now, it looks like both to be the same. That difference which I am trying to highlight here is in this, the damage size is not growing at all. It's a damage initiation phase, we call. In this, the initial damage, AI, if you have defined like a whole, say, this one, then it starts growing, and that's a damage tolerance design approach over here in this case. You are trying to consider how much the damage is allowed to grow before it becomes critical from the residual standpoint of view. In this case, you are considering damage does not initiate. So basically, this is like a safe life here. In safe life also, we say damage is not initiating. So this is like a safe life here. This is damage tolerance. Okay, damage definitions and sizes. Let me just give you the idea about what damages I've been talking about and what is the BVID, VIDs, and all that we talk about. Now, BVID, damage visible from a distance of 1.5 meters in a hazy light with unaided eyes. You don't use any magnification. Just when you're walking, a person walking, and the damage should be visible from a distance of about 5 feet or 1.5 meters. And not in a bright daylight, but even in a hazy light. Then depth. Now, depending upon the organization, then depth could be 0.25 millimeter to 1.0 millimeter for commercial aircraft. This is after the damage relaxation. You try to impact it. Suppose at the time of impact, the damage is 0.3 millimeters, 0.4 millimeter. After 24 hours, that 0.4 millimeter may drop to 0.25 millimeter because it relaxes. Composites are viscoelastic materials, and with time they relax. So what happens? The initial damage, the dent depth would reduce after 24 hours or after 2 days. So when we are putting the size, these sizes are after the damage relaxation. So what happens when we are doing the testing? we will impact today's egg, and we measure the damage. Then we measure it next day, 24 hours, and then next day, and then see how much the relaxation. So usually what happens, suppose we are defining our requirement to be 0.25. So at the time of impact, we will create a bit larger damage because we know that this damage is going to relax. Now, what you see from the diagram, as I was talking, in metal, this damage, if this is a metallic sheet, when you create an impact, the dent will be visible and there won't be any damage like this one, what you see. But in composites, this is a typical. The impact would have created enough damage which is not visible on the surface. No fiber damage or anything, but internally, there's a delamination of fiber damages could occur. So this is a difficulty with this composite structures. The inside damage, but no outside damage may be visible. And say for military aircraft, suppose you're dealing with a military aircraft, the BVID requirement for a military aircraft is 2.5 millimeter. Now 2.5 millimeter is severe requirement. It's quite, in fact, detrimental compared to the commercial aircraft. Impactor, when you are trying to consider this damage, there's a limit prescribed 25.4 millimeter 1-inch steel impactor tip. Maximum energy impact. Now what happens when you're trying to impact, suppose 1 millimeter plate, when you are trying to impact, it would require less energy to create the same dent. If it's 5 millimeter thick, it would require high energy to create the same dent. The requirement is okay. The dent depth is required. However, if it's very thick skin, like a 1/2 inch thick or 10 millimeter, 12 millimeter, you may have to apply almost like 150 joules in order to create less than 1/4 millimeter. So the restriction is put, you don't have to worry about going for a very high energy and still create a 0.25 millimeter diameter indentation. The reason being behind that, to put this limit on this energy requirement for the impactor is because in practice, what was found, a lot of survey was done by Northrop. In fact, for various indenters, hailstones, various damages which could occur in the field or when aircraft is operating, taking off, landing on the airstrips due to some stones hitting the structure. But for all the impacts together, when they worked out, thousands and thousands of tests, they found the maximum energy level which exceeded, which was around, I think, around 50 or 60 joules, 50 pounds. That means around 75 joules or 80 joules maximum could occur in practice with hailstones, everything together. So on a safety side, it was considered to be about 100 foot-pounds in terms of pounds, or in terms of joules, 140 joules per meter square as a cutoff level. So that's a BVID criteria. The dent depth criteria depends on the capital organization, and that's why I said the range is this much. So Airbus could be using different one, Boeing could use different criteria. Delamination entity-dependent holes or notch sizes. Besides this, the residual strength requirement for commercial is ultimate for this damage, but for military is lower than ultimate, you can see. However, you can see the damage requirement is 2.5 millimeter. In fact, 2.5 millimeter, according to my calculation, showed that, in fact, even this load is high enough. Okay, next one, undetectable damages, we consider like holes, notches, delaminations. Holes or notches, normally we consider up to the 6.4 millimeter or 1/4 inch hole. That's a standard for justification, considered as undetectable damage. Delaminations, half inch by half inch, that's the usual considerations, even though, say, when you are doing the NDT analysis using some probes, you might be able to detect around 6 millimeter, 7 millimeter. However, to be conservative, usually the industry practice is to consider half inch by half inch delamination for civilian aircraft. You see the next line, when delamination for military aircraft, 2 inches, which is fairly severe requirement. So residual strength degrades quite rapidly when you have a 50 millimeter circle compared to half inch by half inch damage. However, the residual strength requirements similar to the previous one, the limit, 1.5 into limit, that's the ultimate load for commercial, while 1.2 times the limit for military aircraft. I've just shown schematically the delamination and NDT limitation, holes and notches. Undetectable damages, continuous surface scratches. Military aircraft requirement, JSSG 2006, specifies the minimum scratch to be considered as a BVI, as the undetectable damages, say 100 millimeter long and 0.5 millimeter deep. Why I'm just describing it, but it might be interesting for you, because suppose you are looking into the aircraft like Tejas or your EDA, HL, they would have used these requirements for JSSG 2006, possibly. So it might be useful for you. For civilian aircraft, of course, there's no requirement being prescribed by the FAR regulations. However, industry will specify definitely some requirement for the scratches, surface scratches. It could be 2 inches, it could be 3 inches, it could be 1 ply deep or 2 ply deep. I can't give the exact figures. What the industry will prescribe, because unless it's published, I won't be able to specify. Okay, detectable, readily detectable. So I did talk about detectable damages and RDDs, readily detectable damages. So visible impact damage, which normally the dam depth greater than 1 millimeter. Impactors could be larger here, 100 millimeter tip and 25 millimeter tips. Energy levels, we've said for BVID or undetectable damage, the energy limit was 140 joules. Whereas for this one, there is no energy cutoff. That means, suppose you have half-inch skin, and you want to create the dent depth of 1 millimeter, you might have to apply like at 300 joules or 400 joules of energy. But the requirement would be you would have to create that much dent depth independent of the energy cutoff to satisfy the damage tolerance requirement to show the residual strength for that thickness. And residual strength, of course, is the limit load carrying capability for that. Residual strength P limit commercial note sizes are approximate and may depend upon aircraft type organization. So I just roughly put the sizes. It doesn't mean they're exact sizes. Depends on the aircraft organization. Holes, like at least 4 inches, it could be 6 inches. Large notches, 150 millimeter long, could be more. And depending on the structure, for a fuselage, it could be 12 inches. Detectable, readily detectable damages again, stiffened panel, two-way crack is required, and the stiffened panel, the stiffener disbonds. And residual strength based on the regulatory requirements, it could be 70% of limit, or it could be limit depending on the damage and the organization, regulatory requirements. For defense, military applications, the load requirements are different. There's a table provided in GSSG 2006, that is the military aviation regulations for the damage and the load requirements. Immediately obvious, which is known to the pilot, which occurs during flight. Immediately obvious of damage, which is greater than the residually detectable damages, where no residual strength analysis is required except for damage resulting for in-flight discrete source damage, but it's right, because you require residual strength when the damage occurs to carry or get home load requirement, which is around 70% of the limit load. Okay, now compliance for these damages. When you want, how do you satisfy the requirements? Usually what happens for the category 1 damage, you will recognize the undetectable damage. So in order to satisfy or meeting the compliance for that damage, we normally would use a 1/4 inch hole or 6.4 millimeter hole. For open hole compression value, the open hole tension, filled hole compression, and compression after impact for thin laminates and sandwich. And that is how we'll develop the compliance philosophy. Determine the allowables with these damage sizes and determine that's the residual strength we require at least. Subcomponent by subcomponent test, coupon test, compression after impact test. Categories 2, 3, 4. Design allowables using large damage coupons and panels test data. Subcomponent and component test and analysis methods. Analysis. Any questions so far on these damages? Anyone?
Yeah, Dr. Garg.
Yeah.
When we say readily detectable damage, and if they are to be repaired before the next flight, we said after repair, it should be able to take the design limit load.
Ultimate load.
Now,
yes.
if this is a component of aircraft itself, how is it tested to make sure that it meets that requirement? Is the component tested to that particular ultimate load?
No, it's a theoretical. You know what happens? All these repairs, when we specify, we qualify the repairs by initial testing. Like suppose we are defining, you have a flap. Flap with a thickness of different thicknesses in different regions and different layups. And the damage could be anywhere, suppose. So we have defined, okay, in this damage zone, and this is my damage limit, like you can 2-inch hole or 3-inch hole. And airlines have to repair that 3-inch hole. We provide the repair scenario, how they will repair, what kind of layup they would use, what kind of material they would use. And that repair which we have designed, which airlines will do, will already meet the ultimate load requirement.
Oh, I see. The actual loading need not be done.
No, the thing is, no, because we have given the airlines the repair manual. Okay. The purpose of repair manual is for the airlines that we are defining a damage, that this is a damage if it occurs in this region, you use this repair philosophy.
Right.
So we provide the material type, the thickness, everything is put in the repair manual, and that's a big part of the manufacturing agency, whether it's Airbus or Boeing. When a aircraft is sold, along with that, the repair manual also is a mandatory given to the airline.
Okay, right, thanks.
But there is a restriction also, where repair manual may not be able to define all sorts of damages which can occur in practice. And what happens, Many of the airlines may not have the capability. So quite often, if the damage occurs, they will send a message to, if it's an Airbus aircraft, to Airbus or Boeing, and then they will ask the opinion from Boeing or Airbus, look, this is the damage which has occurred, and what do we do?
Okay.
In fact, I remember one case, one of the several years back, the damage occurred in one of the aircraft structure. The aircraft was in USA, and then I got a phone call right in the middle of the night around 2 o'clock. I had to go to a company to, other colleagues also came to define the repair. And it could happen like that.
Okay. Right.
But yes, once the repair is done, the capability of the structure is returned to the ultimate load carrying capability. Another issue with that repairs is, and we define that, if the repair fails during service, then the residual strength capability of the damage has to be retained to the limit load carrying capability. So there are a lot of issues with when we define the repair. They're not easy. Repair sizes, we design them, and the type of the repairs. A lot of analysis and testing goes when repair manuals are retained by the company. And it's a big task. It's not simple.
Okay.
Okay, so detectable, readily detectable damages. Okay, we define about this one. So, okay. Any other question before I move from here? No. Okay, so I consider, a few steps for the analysis of the structure. I won't go into the details of that, just schematically. So you have a product, CAD, using CAD these days, everything is done by computers, aided design. Those days are gone when a drafting engineer will draw the sketch and then we'll pick up manually, start analyzing the structure. Now nothing is done by hand, it's everything on the computer, CATIA. Normally CATIA, computer-aided design, is used for all the structural analysis. The designers draw the scheme, and directly that can be converted to Nestran or Abacus to analyze the structures. So product CAD geometry, structures for analysis, all interfacing structures, then FEM modeling, mesh geometry, fasten connections, interfacing joints, materials and element properties, aerodynamic pressures, inertia forces, and any other external loads, boundary conditions. See the next slide. Previous slide, okay. Once you have made the FE, the model, and incorporate all the interface loads, interloads, FEM, sorry. This is the output, FE output. So you get the interface loads like reactions between the fittings and the structure. Internal loads, forces and moments, strains and deflections, natural frequencies, and buckling stability behavior. Use the Nestran or Abacus packages usually to analyze the structures. Then once you have got those internal loads and the reactions, interface reactions, the first thing you would do is draw a shear force bending moment and torque diagram. This is fundamental thing. For any structural analysis, we must understand shear force bending moment diagram. That's a classical analysis. Basically what we were taught in our second year mechanics in IITs. And that is always valid. The shear force bending moment diagrams, very important for the structural analysis. And once you have that said, you want to analyze the fittings. Fitting strength analysis. Let me tell you, the fitting strength analysis is still usually done by hand. Of course, hand doesn't mean by pencil paper. We use the analysis tools, Excel spreadsheet for analyzing rather than generating the FAM analysis for the fittings. Usually, of course, it's doubled sometimes. The FEM is also done for the fitting models and hand analysis usually. Say within Boeing, we had lots of tools which they have developed, and you can feed the geometry, various sections for the fittings, and get the stresses of various sections, write the margins under various loading scenario. So a lot of handwork goes on. It's still the classical mechanics. Because for the fittings, normally my experience is FEM analysis, we normally do not rely. Then when you have the internal loads for each element, you determine the ply strains and stresses. Then you analyze the bolted joints, radius interlaminar delamination. I'll talk about these things a little bit in the slides. Holes and notches, buckling and post-buckling, damage tolerance, fatigue, aero surface smoothness, vibration analysis, sonic fatigue analysis. I've just listed a few things for the structural analysis because to give you understanding that when we are designing the structure, we have to consider each of the modes of failures. And all these considerations are there, what I've shown for the structures which you have to consider. I think the best thing is to stop over here and invite more questions, what you have, so that it's a good time to stop and question answers. Okay, let us see if anybody has any questions for today or from previous days, which I could clarify. Any questions?
Sir, actually,
Yeah.
with regard to the failure mode analysis, like how we are identifying that what are the all means different modes of failure? Like, is it like a full system level or in subsystem level itself we are doing some tools like or use something like that?
Failure analysis. Now, suppose you are designing a fitting, metallic fitting. Maybe I could show you some typical example next time. It is like a broom. You know, if you're using a fitting analysis like a broom, what you will do if it's a beam, you know, fitting is like a beam which will have the loading, bending, torsion, axial loads. And you will divide the fitting into different sections, and at each section, you will have the importance here is you have the shear force bending diagram, and then you draw the free body diagram at a section and see at the free body for that section, what are my loads coming up? Now, then using the loads, how much is the bending, how much is the torsion? So shear stress, normal stress, that is what you will do and write the margin, interact the various stresses. So basically everything boils down to your mechanics of solid, what you have been taught in second year, third year of engineering, finally. So it's a fundamental to understand a free body diagram. Maybe I might show you some next time, just to make you clear. about this. Modes of failure. So
okay.
And then composites. Composites, of course, I have listed over here, but I'll show you the slides later on, where first thing is when a laminate is being designed, you have the internal loads coming onto the laminate, or loads like moments and axial forces. Based on that, you will use the laminate analysis, determine the ply strains, and then calculate the margins. Have you been taught the laminate analysis at all?
I have not learned.
Pardon?
I have not learned that. Yeah.
Okay. That maybe the composite structures when is being taught, maybe. But I'll show you some of the things over here, say they are there. But in general, of course, we can't go into too much of depth of each of these. But good question. Might try to make the things more clear a bit. Any other question?
Dr. Gar?
Yeah.
We have been talking about this damage detectable, different types of these. Now, damage as such is a general term. So, do we have separate criteria to analyze each one of them? For example, a crack or a delamination or a hole. Are we dealing with them independently, or we take the most critical type and then go ahead with that?
Well, you have to analyze the hole. Suppose it's a 6-inch hole. You have to consider that the damage, like a notch, like a 10-inch crack in the stiffened panel. You have to analyze that. And it has a lot of issues. In fact, they are not easy to analyze. The methods have been developed, especially in the structure, stiffened structure. Let me just go back. Say, when you are trying to analyze this, it's a layup. So damage normally will be considered initially, say here, this much damage. Then it's considered, okay, I'm loading it, and the damage should be able to propagate right up to this. But beyond this, it is not allowed to propagate. Normally what happens, we consider the damage should deviate, go as delamination, so that the residual strength capability, what we get from after this propagation is like a get home load capability, 2-bay crack, or limit load. So now you're coming back to your question of damages. Damage for composite is very complex. There's no simple solution for large damages.
Yes.
Depending upon the layer, because damage is not progressing a self-similar solution. It's not here I've shown like this damage, but this would be going like this one or this one in any direction, which becomes difficult to analyze. And lots of methods have been developed within Boeing side. They have spent millions of dollars in developing the methods for large notches. I could talk about it next time. And if you go to the NASA website, you may find some interesting papers for large damage analysis based on cohesive elements, which is inbuilt in Abacus now.
Okay.
And many of the papers, I could send you the list of the papers if you are interested in reading them. But if you yourself go to the NTRS, NASA Technical Research site, you'll find lots of papers for large notch damages methods. A lot of work has been done. In fact, this has been a hot area always for last 30, 40 years, damages in composites. And still, it's not easy to predict the behavior.
Right. Okay.
So methods for delamination, through thickness damages, a lot of work has been done, lots of people. The difficulties come over here in the structures when you're using. You have a skin crack is there. The spar is there. Spar also has to be broken on the flanges. Determine the residual strength of that. Doesn't become easy to analyze. And you can't keep on testing every configuration. So that means we must develop some reliable methods of analysis for the large damages. And that's what I was saying. Hundreds of millions of dollars probably Boeing would have spent in developing the methods.
Right. Okay.
I say, because if you develop the right method after validation, and then you have to test also to get the confidence in the methods, and that's the way methods are developed. And in long run, then it makes it cheaper because you have to analyze those structures, the damages created during bird strike or any other damages. And there's a mandatory to cut part of the spar, skin together and try to show the residual strength requirement. So you must be able to analyze it. So it's a big area, and we could discuss it sometimes.
Okay, right.
Any other question?
So I guess there are none. So thank you very much, Dr. Garg. We'll probably catch up on Friday again.
Okay. Can this Friday lecture be shifted to Thursday? Possible?
I have no issues. Let's take a call from the audience. Do any of you have any issues attending at the same time, right, Dr. Garg?
Yeah, same time. You can have the same time.
So
Friday,
can we have it on Thursday at 3 p.m.? Any of you have a conflict? Dinesh?
Only this week or?
yeah, only this week. Only this week. Or Wednesday, I don't mind.
Thursday seems to be fine. Nobody has any obstacle or issue with that.
So let's have it on.
Let's meet on Thursday. Yeah, sure.
Yeah. Thank you very much. Okay.
Yeah.
Bye.
Thank you so much again, Dr. Garg.
Have a good day. Bye.
You too.